All right, this is Similar Polygons continued, so the second part of section 8.1. And in the second part, we will be focusing on finding perimeters and areas of similar polygons, also deciding whether polygons are similar. We have the same essential question from the previous video: how are similar polygons related? All right, let's look at finding perimeters and areas of similar polygons, and we'll start with the first theorem. That's perimeters of similar polygons theorem. States if two polygons are similar, then the ratio of their perimeters is equal to the ratio of their corresponding side lengths. So what that's saying is, when we look at these two figures, that if KLMN is similar to PQRS, then if I were to add up all the sides, so PQ plus QR plus RS plus SP, and compare it to the perimeter of the other figures, so in this case KL plus LM plus MN plus NK, it will be equal to each corresponding pair of sides ratio. So PQ compared to KL, QR compared to LM, SR compared to NM, and PS compared to KN. All of these ratios will be equal to each other. So let's analyze this a little bit further to say that when two similar polygons have a scale factor of K, then the ratio of their perimeters is equal to K. All right, let's take a look at example 4, modeling with mathematics. A town plans to build a new swimming pool. An Olympic pool is rectangular with a length of 50 meters and a width of 25 meters. The new pool will be similar to the shape of an Olympic pool, but will have a length of 40 meters. Let's find the perimeters of an Olympic pool and then the new pool. Let's start by trying to understand the problem. We're given the length and the width of the rectangle and the length of a similar rectangle, and we need to find the perimeters of both. So the plan needs to include finding the scale factor of the similar rectangles and finding the perimeter of the Olympic pool, and then using the perimeters of Similar Polygons theorem to write and solve a proportion to find the perimeter of the new pool. So let's see if we can solve this problem. Because the new pool will be similar to an Olympic pool, the scale factor is the ratio of the lengths. In other words, 40 to 50, reducing to 4 over 5. The perimeter of an Olympic pool is 2 times 50 plus 2 times 25, which equals 150 meters. Write and solve a proportion to find the perimeter X of the new pool. If you're wondering where this 2 times 50 plus 2 times 25 came from, perimeter would be the distance all the way around a shape. And in this case, there are 2 lengths that are 50, and there are 2 widths that are 25. So that's where this came from, totaling a perimeter of 150. All right, so this allows us to set up our proportion. We have X compared to 150 equaling 4 compared to 5. Remember, 4/5 is our scale factor as a ratio. So to solve the proportion, do your cross multiplying. That results in 5x equals 600, and then 600 divided by 5 results in 120. So the perimeter of an Olympic pool is 150 meters, and the perimeter of the new pool is 120 meters. And just a quick study tip, you can also write the scale factor as a decimal. In example 4, you can write the scale factor as 0.8 and multiply 150 to get 120. Let's look at our next theorem, the area of similar polygons theorem. If two polygons are similar, then the ratio of their areas is equal to the squares of the ratios of their corresponding side lengths. So let's look at this theorem in perspective with the two figures given. It's stating that if quadrilateral KLMN is similar to quadrilateral PQRS, then the area of PQRS compared to the area of KLMN is equal to each corresponding pair of sides squared. the ratio of each pair of corresponding sides squared would equal the same as if we had the area of each of the quadrilaterals compared to one another. All right, we can use ratios to find measures or dimensions. So let's take a look at this example where we have a perimeter of a rectangle is 484 feet. The ratio of length to width is a 9:2 ratio. Now find the area of the rectangle. So here's a sketch. We've got the length labeled and the width labeled. And when you are looking at your ratio statement, you want to look to see how the wording is stating the order in which you compare the ratios. So let's look at our second statement one more time. It says the ratio of length to width. So the order matters. We've got length, keyword here to, width. So that means the 9 goes with the length, and the width is the 2. So as far as labels, we want to put the 9x applied to the length, and the width would be 2 times some unknown value x. And now that we have some numbers with our labels, we can set up our equation for perimeter. We've got 2 lengths and 2 widths, so we plug in the 9x representing the length, and then 2x representing the width. And then we know the perimeter is 484, so we replace that capital P with that value 484. Distribute each of the 2's, so you've got 18x and then the 4x, and then combine like terms, resulting in 22x. So then divide both sides by 22, resulting in x equaling 22. So next you would substitute 22 in for our x's, so 9 times 22 results in 198. And then 2 times 22 results in 44. So we now know a length of 198 and a width of 44. So that allows us to figure out our area by multiplying the length and the width, results in 8,712 square feet. Let's apply this same strategy to a second example where we have the measures of the angles in triangle CDE are in the extended ratios of 1 to 2 to 3. Find the measure of the angles. Start by sketching any triangle, doesn't matter, and labeling all of the angles with the 1x, the 2x, and the 3x. And the x, once we solve this equation, will help us with at least one of our angle measures. And then we know that the second angle is twice the size of the first, and the third is 3 times the size of the first. That's what our ratio represents, is a factor or a multiplier. And we know based on the previous unit that the sum of the interior angles of a triangle is 180 degrees. So we can take all of our expressions, 1x plus 2x plus 3x, and total it to 180. And we've got our equation, solving for x, combine like terms on the left side to be 6x equal to 180. Divide both sides by 6, resulting in x equals 30. Now that we know one of the angles, the smallest angle, is 30 degrees, then we double that, we get our next angle, which is 60 degrees, and then we triple to get the third angle, which would be 90 degrees. So our measures are 30, 60, and 90 degrees. Example 5, we want to find the area of similar polygons. So in the diagram, triangle ABC is similar to triangle DEF. Find the area of triangle DEF. Well, what we're given is one pair of corresponding sides. And then we know the area of the larger triangle. It's 36 square centimeters. So let's think about this situation. Since the triangles are similar, we know that the ratio of the area of triangle ABC to the area of the triangle DEF is going to be equal to the square of the ratio of the two sides. So let's set up a proportion that reflects this information. And it's always a great idea to start by setting up your proportion using a simplified statement or a combination of words and symbols to further set up your problem, because then you can just quickly go in and substitute into your simplified proportion with all the words and the symbols. So here we have area of triangle ABC compared to the area of triangle DEF, which is what we stated earlier. And this is going to be equal to the two sides that were given, their ratio squared. Next, we would substitute the values that we know. We know the area of triangle ABC, so we'll substitute the 36. We want to know the area of the triangle DEF, so that remains an A, or shortens down to an A. We know that the length of AB is 10, so we substitute 10. We know the length of DE is 5, so we substitute 5. And then we're going to square that ratio, which results in a 100 over 25. Next, to solve the proportion for A, we would cross multiply. So 36 times 25, and then 100 times A. And then we would divide both sides by 100, resulting in A equaling 9. So what we can say here is that the area of triangle DEF is 9 square centimeters. All right, next we want to decide whether polygons are similar. So let's decide whether the polygon ABCDE and the polygon PLQRP are similar, and then explain our reasoning. So the two things that have to be true in order for polygons to be similar is that their corresponding angles are congruent. Second, that the corresponding sides are proportional. Well, let's look at the corresponding sides first. So we identify the corresponding angles that are marked, the A and the K, that are both congruent. So those adjacent sides definitely would be corresponding. So our first ratio, 12 compared to 8. And then we have another 12 compared to 8, which we don't need to write it again. And then go around the rest of the shape. So then we have 9 compared to 6. Then we have 6 compared to 4. And then we have a repeat of 9 compared to 6. So we don't need to write that again. And then simplify all your fractions. So 12/8, 12 and 8 can both be divided by 4, resulting in 3/2. 9 and 6. Both 9 and 6 can be divisible by 3, so that results in a 3/2. And then our last ratio, 6/4, the 6 and the 4 can both be divisible by 2, resulting in 3/2. So it appears as if our sides are proportional. So next we need to look to see if all corresponding angles are congruent. Well, we know for sure that A and K appear to be corresponding and congruent. So let's go around the rest of our shape and see if that holds up to be true. We don't have any more markings, but I'm looking at corresponding angles E and P. And it definitely appears as if P is smaller than angle E. And then when I'm looking at R compared to its corresponding angle D, those appear, R definitely appears to be greater than D. So it appears as if our corresponding angles are not congruent. So just because the corresponding sides of our polygon, in this case pentagon, are proportional, the scale factor, same scale factor of 2/3, and because the pentagons do not appear to have corresponding angles congruent, we cannot conclude that the figures are similar. So if we had a dilation with center A and then a scale factor of 2/3, that could move ABCDE onto AFGHJ, so a new polygon. Then a reflection could move that AFGHJ onto KLMNP, as illustrated here. So KLMNP does not exactly coincide with KLQRP, because not all corresponding angles are congruent. So only angle A and angle K appear to be congruent. So because angle measures is not preserved, the two pentagons are not similar. And that's all for this lesson with similarity using perimeter and area. So we'll practice next class.